Welcome back to eCoreAcademy, students. My name is Anita Raj, and I am one of the teachers and co-founders here, along with my younger brother, AJ Raj. Today, as you can see, we have a new Algebra 2 lesson, and we're going to be finishing up our series on rational functions and their graphs. Like I promised in the last video, I'm going to dedicate this entire video to practice problems. So we'll be concluding this series of lessons, as it says on the screen, by doing four main things. First thing we're going to do is we're going to review how to graph rational functions. What we're mainly going to do is we're going to review how do we find holes, vertical asymptotes, and horizontal asymptotes. And I have a clear set of instructions written out for you so you can use it like a play-by-play whenever you're approaching one of these problems. Afterwards, we're going to identify some discontinuities without graphing. So I'm just going to find some equations of rational functions, and we're going to look at them, and without graphing them, we're going to identify if they have any holes, vertical asymptotes, and or horizontal asymptotes. Afterwards, we'll do graphing practice. We'll do one graph where it's pretty much what we've seen so far. A rational function that has one horizontal asymptote, one vertical asymptote, and a hole. And then I have a special example where you're going to see somewhat of a parabola form, and then you're going to see two curves as well. And that's going to have two vertical asymptotes, something we haven't seen, but something that's very much possible. Remember, our only requirement is that we have at most one horizontal asymptote, but we can have multiple vertical asymptotes. And then afterwards, we're going to conclude with a pretty simple word problem. And I'm going to be incorporating the TI-84 graphing calculator into this. So if you don't have one on you right now, I would grab one for sure. I'm not going to show you like a demo of it because it's pretty much something we've gone over and over and on, something we've used over and over again, which is mainly intersection of graphs. So I'm not going to show you how to do that, but I'll walk you through it because that's something you should be able to do by now. All right, so before we get into the video, there are two things I want to do. I want to just nod at the little image I have on the screen. It says asymptotes, a danger to our children, and you can see that we have a graph that's focused around the origin, and you have two curves that are kind of meeting each other, but they're not quite touching. They're just decreasing without bound. They have a limit of negative infinity because they just are going downward. The function of the value is just decreasing, and then we see that we have a vertical asymptote at x equals 0, which is the y-axis. And you see a parent standing on one of the curves going, no. And then you see the child actually sliding down the curve going, we. So the child's treating it like a slide, but really, it's like this funnel or vortex, and the child's going to get caught in it. So I thought that was pretty funny. Hopefully you get the joke. Before we get into the video, I'd really appreciate it if you could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Okay, let's jump right into the video. Like I promised, we're first going to be reviewing how to determine and graph holes, vertical asymptotes, and horizontal asymptotes. So let's first talk about how do we find holes in a rational function. First, what you want to do is you want to factor everything and determine when the denominator equals 0. So if we have f of x equals p of x over q of x, you want to factor, and p of x and q of x are both polynomials. You first want to factor p of x and you want to factor q of x. And then you want to take the factors of q of x, which is the denominator, and set them each equal to 0. There are multiple factors. For example, if we have only one factor, like a linear factor, like for example, let's say p of x equals 4. That's going to be your only factor, and to find the 0, you would set x equals 4 equal to 0. However, if it's maybe a quadratic trinomial and you factor it using like a guess and check method, you find that factored p of x is equal to x plus 2 times x minus 3. So you would set each of those factors equal to 0, and then you would solve for two different zeros because that polynomial q of x would have two different zeros. So you're going to set the denominator equal to 0 and find the zeros, solutions, x-intercepts, roots, whatever you want to call them. So that's what you want to do first. And then you want to reduce your function. So if you factor p of x and you factor q of x, you want to see if they have common factors that you can cross out. That means they cancel out. And you want to pretty much reduce means simplify. So you're trying to factor, and then you're trying to do some basic division by canceling out common factors between p of x, which is your numerator, and q of x, which is your denominator. Then you want to try to substitute your points of discontinuity into the reduced function. Right now, the points of discontinuity you found are the factors that you actually set, the factors that you found in the denominator. So whenever you set the denominator equal to 0 and you set those however many factors in the denominator equal to 0, and you found all those all those points of discontinuity. Now you have to determine, are those points of discontinuity vertical asymptotes or are they holes, because they're going to fall into one of these categories. So for example, if we have something like, I'm just going to give you an example that we're actually going to go over later on in this presentation. If you have an example like y equals the quantity y equals the quantity x plus 6 divided by the quantity x plus 6 times x minus 6. So x plus 6 is the numerator, x plus 6 times x minus 6 is the denominator. What you're going to do is you're going to set the denominator equal to 0. So you would set each x plus 6, you set x plus 6 and x minus 6 equal to 0, and then solve. And pretty simply, you can find that your zeros would be 6 and negative 6. But because we have an x plus 6 in the numerator, those two, in the x plus 6 in the numerator and denominator, would cancel out, and then you'd be reducing your function of y equals 1 over x minus 6. Then when you find those points of discontinuity, like we said before, by setting the denominator equal to 0, we found the points of discontinuity to be x equals 6 and x equals negative 6. What you're going to do is you're going to plug those points back in to the rational function, which is going to be which is the original rational function. And then you're going to determine, based off of what you find, you're going to determine if it's a hole or if it's a vertical asymptote. If you are able to substitute them in, then it is a hole. So I'm going to actually write this out for us. So let's say we have the rational function y equals x plus 6 over x plus 6 times x minus 6. Let's say we simplify, let's say we set the denominator equal to 0, and we found our zeros, our points of discontinuity, to be negative 6 and 6. And then let's say we get the numerator and denominator factors in them both to cancel out, and we get 1 over x minus 6 as our reduced function. What we're going to do now is we're going to substitute these points back into y equals x plus 6 over x plus 6 times x minus 6. If we substitute negative 6 back in, what happens is our numerator is going to become 0, so we're going to end up getting y equals negative 6 plus 6 over negative 6 plus 6 times negative 6 minus 6. The numerator is going to end up being 0, and then whatever's in these set of parentheses is going to be 0, and then here we're going to have a negative 12. However, because 0 times any number is 0, we're going to end up having 0 over 0. Whenever you have 0 over 0, always going to indicate that there's a common factor. In this case, our common factor was x plus 6. In this case, we were also able to substitute. Like, this is perfectly fine. Our answer is equal to 0. We didn't violate any rules with zeros. Like, for example, you can't divide a number by 0. So because we were able to substitute, we know that x plus 6 or x equals negative 6 is where the hole occurs. If you're not able to substitute, it's a vertical asymptote. So in this exact same case, I'm not going to write it out because hopefully you get it at this point. If we were to substitute 6 in for x, we would end up getting y equals 6 plus 6 in the numerator over 6 plus 6 times 6 minus 6 in the denominator. In the numerator, if we added the 6's, we get 12, and then in the denominator, if we added 6 plus 6, we get 12, but then the second set of parentheses, 6 minus 6 is equal to 0. So 0 times the 12 in the denominator would be 0, and then you'd end up getting 12 divided by 0, and that can't happen because we can't divide a number by 0. In that case, we wouldn't be able to substitute, and our answer would be undefined. Since we were not able to substitute, x equals 6 is where the vertical asymptote discontinuity occurs. And if nothing cancels out, then there is no hole, meaning when we reduce the function, we factor those two polynomials. If nothing cancels out, let's say in the numerator we didn't have an x plus 6, let's say we had an x plus 3 in this case, then there would be no common factors, there would be no canceling out, meaning there is no hole. There's just going to be two vertical asymptotes because of the two factors in the denominator. All right, let's move right along. How are we going to find asymptotes? So to find vertical asymptotes, remember vertical asymptotes go up and down like this. And usually we draw a hatched line like that on a graph. And their equation is x equals some constant. So x equals c. And that's how you would write the equation of a vertical asymptote and draw it on a graph. So how do we find vertical asymptotes? So first you want to find the reduced denominator if it reduces. So if you have q of x as your polynomial, you're going to factor it if it is factorable, and then you're going to determine when it's equal to 0. So if it's factorable, you're going to set your factors equal to 0 and then find the zeros. If it's not factorable, then just set the denominator equal to 0 and see if you can find any real solutions. Then you want to check to see if it's a whole and not an asymptote, because remember, a discontinuity cannot be both a whole and an asymptote. If a hole occurs somewhere, there's going to actually be like a single hole at that point, but the graph continues after it. The hole can't occur right where an asymptote is, because the in both cases, the function has no value where that discontinuity occurs. The function doesn't have a value at a hole, and a function doesn't have a value at an asymptote. But you can't have a hole occur on top of an asymptote, if that makes sense. So you're going to use the methods we talked about on the last slide to check if it's a hole, and if it's a hole, then it's not an asymptote. That's really simple with asymptotes. Your vertical asymptotes, you're really just focusing on the denominator. As long as you're going to get rid of the common factors, cancel them out, and then focus on whatever is left in your reduced function in the denominator. To find horizontal asymptotes, well, before we get into that, remember horizontal asymptotes go like this, like the horizon, like the sun on the horizon, and then their equation's y equals some constant. All right, so what you're going to do when you look for horizontal asymptotes, you're going to look for the highest power of x. What do we mean in this case? Well, usually we're working with polynomials, which are linears, and then above. Sometimes we'll have constants. If you have a constant, then you automatically know the power of x is going to be 0, because let's say we have a constant, let's say we have 2 in the numerator. Then what is the power of x in that case? Well, 2 is pretty much equal to 2 times x to the power of 0. And x to the power of 0 is 1. So it's pretty much 2 times 1, which is 2. So you're going to look for the highest power of x in comparing the two polynomials, p of x and q of x. If the highest power of x is found in the denominator, meaning you're comparing the degrees of both the polynomials, if you find the highest power in the denominator, then you automatically know there's a horizontal asymptote. For example, if we have something like x plus 4 divided by x squared minus 2, there's an x squared in the denominator, which is the higher power. So in this case, the vertical asymptote is going to be y equals 0. If you want to think of it like if you rewrite the I don't know why this makes sense to me. It doesn't really make a lot of sense, but it's just the way I think about it. Whenever you reduce a rational function, if you think about it, let's say you think about it this way: if you could factor both the numerator and denominator, and then you could cancel out a common factor, and whenever you're left with like 1 over something, whenever you're left with like a fraction. For example, in the last video, we talked about y equals 1 over x, how y got more and more small as x increased. It's just a similar thing. So whenever you think you're going to be left with a fraction because the denominator is bigger, then you're going to have a horizontal asymptote at y equals 0. If it's both, so if the degrees of both the numerator and denominator are equal to each other, you're going to use the coefficients of the highest power of x. So you're going to order those polynomials, if they're not in order, in descending order. You're going to pick the leading term in each, and then you're going to determine what are the coefficients. So the coefficients of the leading terms, the coefficient of the leading term of the numerator is a, and the coefficient of the leading term of the denominator is b. Then you're going to divide a by b, and whatever you get, whatever fraction you get, usually you'll get a fraction, sometimes you'll get a constant, is going to be equal to your vertical asymptote. So y equals a over b. And then lastly, I'm sorry that it's kind of overlapping, but if the highest power is in the numerator, meaning let's say we have an example like that same example with the x squared minus 2, but let's say we flip it, and this time we have x squared minus 2 in the numerator, and then we have the x plus plus 4 in the denominator. The numerator has a higher power, and if the numerator has a higher power or a higher degree, then you're going to have no horizontal asymptote. Okay, so we're gonna do some problems. We're not gonna do any graphing in these problems. That's why I call it the no graphing problems. So for these problems, we're gonna find the vertical and or horizontal asymptotes. We might have both, we might not have both, and then we're gonna see if any holes exist. In these scenarios, you're not gonna have to graph. So let's just go through these examples pretty quickly because I know we've done quite a bit. So we have the rational function y equals x plus 6 divided by x squared minus 36. The first thing we want to do is we want to reduce the denominator. So we're going to factor x squared minus 36. Hopefully you notice that this is a difference of squares. So I'm going to write that over to the side. Difference of squares. As you can see, we're incorporating skills we learned in previous units. Difference of squares. And a difference of squares occurs when you have a squared minus b squared is equal to a plus b times a minus b. In this case, x squared is a perfect square, and 36 is a perfect square. So when we factor that, we get x plus 6 times x minus 6. The middle terms, which is just the constant with an x, which is like your b of x middle term, is going to cancel out, and that's what leaves you with the difference of squares. As you can see here, this is going to be our new denominator. So I'm just going to write this underneath x squared minus 36, so x plus 6 times x minus 6. And as you can see, x plus 6 is a common factor in the numerator and denominator. So we're going to pretty much disregard this for now because that means there's a hole, so this does not qualify as a vertical asymptote. And what we're doing here first is finding the vertical asymptote. So we're just going to focus on the x minus 6. So then when we set x minus 6 equal to 0, we add 6 to both sides, we find the vertical asymptotes x equals 6. Pretty straightforward. Now we're going to focus on that common factor that canceled out, which was x plus 6, to find the whole. So we're going to set that equal to 0, and we're going to subtract 6 from both sides and find that the whole occurs at x equals negative 6. But remember, when we're trying to find a whole, we have to find the corresponding y-coordinate because it's a specific point. So then what we're going to do is we're going to reduce the function. When we reduce the function, we end up getting 1 in the numerator because the x plus 6 in the numerator cancels out with the 1 in the denominator. We end up getting left with y equals 1 divided by x minus 6. The x minus 6 was our vertical asymptote that didn't cancel out with anything. Then we're going to plug the whole, which is negative 6, into our reduced function. So f of negative 6 equals 1 divided by, we're plugging negative 6 in for x, 1 divided by negative 6 minus 6, and then we're going to be left with negative 1 divided by 12. And our whole is going to be at the point negative 6, and the y-coordinate would be negative 1/12. Our degree, to find the horizontal asymptote, we're going to compare them. Our degree is going to be, we're going to compare the numerator and the denominator of the reduced function, and we're going to see that the denominator is x minus 6, and the numerator is 1. So the denominator has a greater degree than the numerator, because the numerator has a degree of 0, numerator has a degree of 0, and the denominator has a degree of 1, so then our horizontal asymptote is going to be y equals 0. Okay, so we're going to move on to the next problem. We're doing the exact same thing, but just with a new rational function. This rational function is y equals 2x plus 3 divided by 5x minus 10. First, what we're going to do is we're going to take the denominator and try to reduce it. In this case, we have 5x minus 10. We're going to pull a 5 out. So if we pull a 5 out, we get 5 times x minus 2. If we distribute that 5, we're going to get the 5x minus 10. Then we're going to set 5 times x minus 2 equal to 0, and we're going to try to isolate x. So we're going to divide both sides by 5, and 0 divided by 5 is 0. So then we end up getting x minus 2 equals 0. To get x by itself, we add 2 to both sides, and we find that our vertical asymptote is x equals 2. So what about wholes? If you look at the numerator and denominator, we can't really simplify anything more in the numerator. We can't factor it or reduce it. And you can see that there are no common factors between the numerator and denominator even after reducing. So there are no common factors, which means that there are going to be no wholes in this rational function. Lastly, we have to determine what the degrees are, so we're going to compare the degrees of the numerator and denominator. If you see, both of them have a degree of 1 because of that leading term of 2x and then 5x. So if you set those are equal to each other in regards to degrees, so we're going to find a and b and then divide them to find our horizontal asymptote. So a is equal to the leading coefficient of the numerator, which is going to be 2x, so the leading coefficient is 2. Then b is going to be equal to the leading coefficient of the denominator. We're going to focus on 5x, and the coefficient's 5. So then to find a divided by b, we're just going to divide 2 divided by 5, and that's 2/5. So our horizontal asymptote is y equals 2/5. Last no graphing problem. So in this problem, we have y equals 4x minus 16 divided by x squared minus 3. First, we're going to reduce the denominator and then set it equal to 0. So if we do that, we get x squared minus 3 is equal to 0. We can find x by adding 3 to both sides. So we get x squared equals 3, and then we take the square root of 3, and we have to take the principal square root and the negative square root. So we find that x is equal to positive or negative square root of 3. So the vertical asymptote, we're going to have 2 of them in this case. One is going to be at x equals the square root of 3, and the other one's going to be at x equals the negative square root of 3. Then we're going to try to simplify the numerator and see if we can find any common factors if there are wholes. So we're going to simplify 4x minus 16 by pulling out a 4, and then we'll get 4 times x minus 4. As you can see, there are no common factors, so we're going to have no wholes at all. Then we're going to do our degree comparison. So the degree of the numerator, 4x minus 16, is 1 because of the x. And then the degree of the denominator is 2 because x squared minus 3, well, that's a quadratic degree of 2. Because the denominator has a higher degree than the numerator, we are going to have a horizontal asymptote, and it's going to be at y equals 0. Alright everyone, so I'm going to cut this video off for now, and then we're going to continue with an extension in the next video where I'm going to be going over graphing problems, and then I'm going to be going over that word problem I was talking about. I hope you enjoyed, and please check out that other video because it does include important information, but I wanted to break it into 2 bite-sized chunks for you. Alright, if you enjoyed this video, please give it a like. Please also, please subscribe, please hit the post notification bell, please comment down below, and please share using our socials. Thank you, and please check out that next video. Bye.